All right, we're going to start this video talking about pull. We talked about momentum in episode 2. So remember, momentum is a product of an object's mass times velocity. A fun way to think of momentum is it's the amount of oomph something has. A giant boulder sitting on the ground has 0 momentum, but a tiny bullet moving with a high velocity has a lot of momentum. All right, so we're going to talk about specifically in this video collisions between objects. So I'll get rid of that. And we'll start with pull. So in this clip, you're going to see the white ball here is given some energy by this stick, right? It applies a force over a distance, gives this ball energy, but the ball also has momentum, has a mass, and it has a velocity. When it collides with the black ball, you will see that some of that momentum is transferred. Now, you won't be able to tell from this video, but we'll see later on that in a collision like this, which, by the way, a collision of this type is called an elastic collision because the objects do not stick together. Okay, so, all right, so let's watch this and see what happens. We had this situation. We had 2 billiard balls. Ball A has an initial momentum, which we'll just say MVA, and ball B, MVB, and this is amount 0. We don't know this amount. They collide, and momentum is transferred. Okay, so what would this look like if we had the numbers? Well, it would look something like this. We have the mass of each of ball A and the mass of ball B, and this is all before the collision. Before the collision, ball A has this velocity, so the product of 0.16 times 4.5 is 0.72. Ball B is not moving, so it has 0 momentum. After the collision, ball A slightly moves, as we saw in the video, maybe with a small velocity of 0.11, and then ball B has a velocity of 4.39. But if you look at this, the momentum of ball B plus the momentum of ball A equals the initial momentum. And that's what we mean when we say momentum is always conserved. The sum of the momentum in a collision will always be the same before and after the collision. This leads us to another equation, which is given here, and you can include on your Season 6 equation sheet. For an elastic collision, this is the momentum of the 2 objects before the collision is equal to the momentum of the objects after the collision. But this isn't just the case when one of the objects has momentum. As we saw in the video, the 1 billiard ball had momentum. This can also happen for objects that are both at rest and are pushing away from each other. Let's look at a quick video. This isn't in a collision in a typical sense, but let's imagine a case where you have 2 ice skaters, mass 2 and mass 1. We'll assume his mass is a little bit greater, right? So the initial momentum before they start skating is 0. So that means the momentum when they're done skating will also have to be 0. Now you might ask, how is that possible? But let's remember that after they push off, they're moving in opposite directions, and we can see her velocity is slightly greater. But since they're moving in opposite directions, one of them will have a positive momentum, one of them will have a negative momentum, so those two could add up to be 0. Let's take this concept for a spin. No pun intended, because it's an ice skating joke, because they spin as they skate. So no, let's take it for a spin. Okay, so we have the mass. He's 60 kilograms, and she is 50. And he has, after they push off, he has a speed of 10 meters per second, or velocity. What is her speed? Let's find it. So using our equation, let's find their initial momentum. That's very easy. They both have a velocity of 0. So I can say total initial momentum is 0. After the push-off, I see that his momentum, and we're going to have to define a direction as positive. So let's define to the left as positive, to the right as negative. So he has an initial momentum, or sorry, after the collision, he has a final momentum of 60 kilograms, right, times his speed, which is 10 meters per second. And her momentum, we know, is going to be negative because she's moving the opposite direction. So it's going to be negative x, or 50, or minus 50 times x, right, which is her velocity. So this is her velocity. She's object 2. Oh, actually, she's object 1. So this is object 2 here, and this is object 1. But they have to equal 0. So now we can solve this for her velocity. We can add the 50x to the other side. We end up with 50x equals 600, and we can divide that, and we can see that x is 60 over 5 meters per second, and that is to the right. I'm not going to put a sign on it. I could put a sign on it, but I'll just give it a direction. So her velocity is 60 over 5, or 12 meters per second to the right. Okay, so that's one type of momentum problem. So let's look at another type of collision that's called inelastic, and we're going to go to outer space for this. So here we're going to go to outer space, and we're going to look at the collision between two tennis balls. First, you're going to see an elastic collision where the tennis balls don't stick together, and then you'll see a second type of collision, which is called an inelastic collision. And that is when the tennis balls stick. So let's watch and see what happens in space.
Which in this case happen to be of equal mass, whether one of them is moving and causes the other to move, or they're both moving and collide and move off in different directions, the total speed and the total mass of the entire system always remains the same. So for example, if this had a velocity of 0, and that had a velocity of 1, the first one might impart some of its momentum onto the second, but the total between the two remains the same. And that remains the same whether one remains still and the other comes to collide with it, or whether they're colliding with each other. It even works, in this case I put Velcro, it even works if these two stick together, the total momentum remains the same. So for example, if I can get these two to stick together while one is stationary and the other is moving towards it, once they stick together, the total momentum will remain the same, so the combined objects will have half the velocity of the one initially that was moving.
Okay, so that's in the case of an inelastic collision. It turns out in most collisions that happen in the world that are neither perfectly inelastic or elastic. There's some combination between the two, and that's because when you have a collision, the object that's being collided with deforms a little bit, or it gets compressed. So mathematically, the equation for an inelastic collision looks like this. You have your initial momentums, and they equal a combined mass times a final velocity. So let's give these cars both mass and velocities. So I'm going to give the cars this initial condition where car 1 has a mass of 100 kilograms. Car 2, the red car, has a mass of 200 kilograms. The initial velocity of the cars is 10 meters per second. And of car 1 is 10 meters per second. And the initial velocity of car 2 is 3 meters per second. It's negative because it's to the left. So we'll define to the left as our negative value. The cars are going to collide and they're going to stick together, okay, like in a car crash. And we need to figure out what will the final velocity be of the cars as they are stuck together. Which way will they move? What will the momentum be? So we can use our equation here where we find the initial momentums of the individual cars, and that's equal to a combined momentum for the cars after the collision, because this is an inelastic collision and the cars will stick together. So I'm going to set this up as M1 V1. So that's going to be 100. Actually, let's do that down here to give us more space. So I'm going to do M1, which is 100 kilograms, times the initial speed of car 1, which is 10 meters per second. And I'm going to add that to M2, which is 200 kilograms, times V2, which is a -3. Negative is the direction. and that's going to equal a combined mass. So after the collision, so actually let's stop here and let's calculate this. So I do this math. It's simple in my head. 100 times 10 is 1,000, right? So we've got 1,000 minus 600. So we end up with a positive momentum of 400. The fact that it's positive tells us that after the cars collide, they're going to continue to go to the right, since we earlier defined this direction as a positive direction and negative direction was this way. Since the momentum is positive, that tells us they move to the right. How far do they move to the right? Well, we have to treat the cars now as one object with a mass of m1 plus m2. So this new momentum of 400 equals 100 plus 200. And we can solve for the final velocities of the cars. When we do that, we get a velocity final of 400 divided by 300, or 1.33 meters per second. So that is how you do a inelastic collision problem in physics.